In the previous session, we have derived the formula delta E equal to I omega square and Cs, where I is moment of inertia for the flywheel, and this omega is average angular velocity of the flywheel, or we can say it's a average angular velocity of the crankshaft also, because this flywheel is connected to the crankshaft. And then this is the coefficient of fluctuation of speed. We have already seen why we define coefficient, which is a non-dimensional number, instead of just going for the actual values. We have already discussed in the previous session. So we we to calculate this one, we need to know I. So how to calculate I? This I is depends on the shape of the flywheel. So what are different shapes, what are different flywheels that generally in use? Different flywheels. First one we generally come across is the solid disc. So this is the solid disc. This is a solid disc, and for example, this is the origin, and this is the y-axis. This is the x-axis, and this z-axis is perpendicular to the x and y plane. So always we go for this notation. This is a right hand notation. So if you turn your right hand from y to x to y, then your thumb should point towards the z-axis, positive z-axis. So sometimes people may take this as a x and this is y, and they may get confused, but you always stick to the right hand thumb rule. And for a disc, we already derived that I x equal to m r square by 4, that is equal to I by y. These formulas we derive in the engineering mechanics. So here we directly take the formula without not going much details. And Iz, then what is the Iz? Z, moment of inertia about axis z, that is going through this center and perpendicular to the plane of the disc. So by using perpendicular axis theorem, Iz equal to Ix plus Iy, but this is 2 times of mr square by 4. That means this is m r square by 2. And another one popularly that is in use as a flywheel is this one. This is a hollow disc, or sometimes we call it as a ring. So in this one, the solid disc, this whole mass is distributed throughout this disc, but whereas here this mass is distributed only at the edges, or at the outer edge. So this is how it's distributed, and for example, if it is a center and this is connected like this. So this is again the center, and again we have I y axis here, x y axis, and this is the x axis, and z axis, that is perpendicular to xy plane, and it's a perpendicular to xy plane and passing through the origin O. So here Ix equal to Iy equal to m r square by 2, and Iz, the you using the perpendicular axis theorem, you Iz is the addition of Ix plus Iy. That means it's a 2 times of mr square by 2. That means m r square. So this is equivalent to the moment of inertia of a ring. So these are the two popular flywheels that are in use, and sometimes we may come across another type of flywheel, that is a torus type. So if it is a torus type, then we'll see what would be the IZ. So torus is like a donut. If you ever eat a donut, this that exactly looks like a torus. Or in India, maybe we can compare the torus with a vada. So if you in vada, that is a round circular one, and in between we have hole. So this is the torus, and for example, this is any circle. If you take at any cross section, this is a circle, and for example, if I take at this section, and if I cut this one, if I cut at this place and look from the top, then that will look like a circle. Or how can you how can you generate a torus? For example, in a plane, I have a circle like this, and I have an axis like this in a plane. That axis is perpendicular to the plane, and if I rotate this circle about this one, then it produces the torus. So, for example, if you take radius of this circle as a r, and distance from the center to the center of this one is a capital R, then moment of inertia about the z-axis is given as Iz equal to 3 by 4 small r square plus capital R square. This is the radius of gyration into mass. Even in the previous chapter, I forgot to mention that R stands for radius of the disk. For example, if it is a ring, then again R is the radius of the ring. So here, what we need to remember is this capital R is not the radius from this center O to the outer ring, but it is the to the center of this particular circle. I have cut this one at this position A dash, and we can see a circle, and this capital R is from distance from O to this center of the small circle, and small r is the radius of the small circle. So these are the three possible or popular types of flywheels that are generally in use. And whenever in the problem he mentions that if he is using the solid flywheel, then we need to mm, take moment of inertia as a mr square by 2. And if you mention other types, then we will take appropriate moment of inertia. And mm, this this is the omega square and the cs. So if he gives this moment of inertia and angular velocity, that is the mean angular velocity, and the coefficient of fluctuation of velocity, then it's very easy to calculate delta E. But most of the time, instead of giving these uh, terms directly, he simply he simply gives some bending momentum diagrams. So how to calculate bending momentum delta E for different bending momentum diagrams. So that we will see for different types of engines. Let's start with the two-stroke double acting engine. We have already drawn bending moment diagram for the two-stroke double acting engine as in the figure. So here it's a completing its cycle in 2 by radians. So uh, this uh, this torque is this is the torque, engine torque produced by fuel burning. So this is starting from 0 and attaining the maximum, it is that is the T max, and then again going downwards and touching 0 again at the pi, and the same way it's again repeating itself from pi to 2 pi, and this is mean torque that is demanded by the output load. We have already seen in our example where a car is going with a 4 person inside. So how how to calculate fluctuation of energy in this case? We have already seen fluctuation of energy delta E equal to I omega square Cs. That means delta E is our energy. For example, if you take kinetic energy, that is half I omega square. That means this energy is proportional to the omega square, or we can say energy is proportional to omega for that fact. So let's see delta energy. This delta E is, as we already defined in the previous session. What is the delta E? This is the difference of E1 minus E2. But whereas E1 is energy corresponding to the angular velocity, maximum angular velocity of the flywheel or crankshaft, and whereas E2 is the mm, minimum energy, kinetic energy corresponding to the minimum angular velocity of the flywheel or crankshaft. So, for example, if the crankshaft is rotating and with a let's draw a diagram for the crankshaft speed. This is the crank speed, and this is turning angle. So we would like to see how crank speed is changing with respect to the turning angle. So for example, this is the mean speed, and because we are taking that crankshaft is already attained some velocity, and we are considering at that particular instant. We haven't considered at the rest. You can consider at the rest also, but here I would like to consider after the engine already executed some certain revolutions. So for example, let's say at this position it is having some velocity something like this. It's starting its velocity here, and let's draw these points exactly here. This is the F point, and this is the G. This is F, this is the G, and this is H, and this is K, and this is M. So we will try to see how velocity of the crankshaft is changing with respect to the crank angle. So let's say it's starting from some unknown value here, and by the time it's reaching crank speed is decreasing because this area is deficit area. This area is deficit and this is a surplus area. So when it is a deficit area, flywheel is providing the energy. That means flywheel speed is decreasing. So for example, at F, the speed at F is less than the starting position O. So for example, if you consider like this, it's going like this, and from F to G, by the time if you go from F to G, the speed is increases. Why? Because here we have a surplus amount of energy that will be given to the flywheel. In turn, that flywheel gets the angular velocity. So here this is the G, and for example, if it is gaining velocity like this, and you connect this one, it reached this one. This is at the position of G, and if when the crankshaft is rotating from G to H, again we have deficit area. That means we need to get energy from the flywheel to the crankshaft. That means flywheel is giving away its absorbed energy, that so that its velocity is decreasing. So at velocity H, and if you compare this area and this area here, this area G area between GH is much more greater than area between O, F or E, if you consider this as a E. So here velocity at the end of the turn or at the H is much more less than F. So for example, if it is this point and you connect these 2 points, this would be like this. And again, when crankshaft is moving from H to K along this path, again we got surplus energy area. That means the flywheel is gaining the energy. Again, we get this crankshaft speed above the mean value. Let's say it is something like that. So you connect again these points, and again at the point M, it's a reducing its a speed. So it will be like that. So if you observe here, this is the mean speed omega m, and speed of the crankshaft is fluctuating, and we don't know what is the minimum speed, but in this case this would be the minimum. Either this can be the minimum or this can be the minimum. For example, if I say this is the omega f, and this is omega h, and this is the omega g, and this is omega k, corresponding to their respective points. So here del E1 corresponding to the energy at maximum angular velocity. Either this could be the maximum or this could be the maximum, and E2 is energy corresponding to the minimum velocity. Either this could be the minimum velocity and this could be the minimum velocity. So if this is the and so if this is the minimum velocity and this is the maximum velocity, then we need to, so if point F is the minimum and point G is the maximum velocity, then we need to calculate E1 here and E1 at G and E2 at F, and the difference between that one gives the delta E. In the other way, if you extend these lines to the original bending moment diagram, this is the area. So this is the area that gives the fluctuation, maximum fluctuation of energy. This is not only fluctuation, this is the maximum fluctuation that we are talking. So this gives the maximum fluctuation of energy. Or if it is not, and if this is the maximum and this is the minimum, I mean minimum, if minimum velocity is at the point H, if minimum velocity point is H, then we need to take this one, area between this one, and if this is the maximum and this is the minimum, then we need to take this one. So here, instead of drawing this whole crank speed versus theta diagram, we can say from this diagram that the area deficit and fluctuation areas, this is the minus one is the deficit and this positive one is the um, excessive areas. So the areas, fluctuation areas around the mean torque, whichever having the maximum area, can be directly taken as the maximum delta E. So for example, if this area is the maximum, so if this area is the maximum, then we can take directly this as the fluctuation, maximum fluctuation of energy, the area above this one above this one. Or if this area between G and H is the maximum, then we can take directly this is the maximum. Or if it is, if the area above the main torque between H and K is the maximum, then we can take this extra area as the delta E maximum. So either way we can calculate. This is how we should calculate for the two-stroke or double acting. Even for the four-stroke also, the same procedure will be applicable, and we will see how to calculate that one. Now we will consider four-stroke one-cylinder engine, and this is that bending moment diagram for this one. and this part is suction, and this is a compression, and this is the expansion or power stroke, and this is again exhaust. So here we this is the deficit area, and this is also deficit area, and this is surplus area, and again this is the deficit area. So we need to calculate delta E here. So what is delta E? This is the delta E maximum. So we know that this part will be turn out to be the delta E, and we will see how that can be deduced from the um, crank speed versus theta diagram. So here we will see this as a crank speed. Let's say this is the mean speed of the crank. This is the omega m mean speed, and I will draw equivalent points on this one. This is the A, this is the B, and this is a C point, and this is the C, this is the D point, and this is the E point. Let's say, for example, if the crank is rotating with the initial velocity omega, and it is starting from this one, this is the starting one O, and at A, and velocity of the crankshaft should be less than the O. For example, if O is like here, O is here, and velocity, this is the A point should be on this line, and for example, this is the A, and you connect these two. Why? Because here this is the deficit area, and the energy stored in the flywheel would be given to the crankshaft to achieve the required minimum torque condition. So that means flywheel and as well as crankshaft are decreasing. So by the time it reaches the point A, the velocity is less than the velocity at the point 0. And if you take point B, here we got a little bit of energy surplus area, so that by the time it reaches the point B, the crankshaft speed is little bit more than the velocity at the A. So for example, this is the B, then this is the B. And if you take point C, this is the point C, we have again one more big deficit area. That means if you compare this deficit area with this deficit area, this is more. So velocity of this velocity at point should be less than both O, A and B. So for example, this is the point and you join this line. Why? Because here more energy should be provided by the flywheel to the crankshaft. And if the crankshaft is going from point C to D, again we got the surplus area. So the surplus area provides energy to the flywheel. In turn, flywheel will absorb some energy. So this is the point here, and if you consider point A like here, and you connect these 2 points, this is the D point. And when the crankshaft is rotating from point D to E, again we come across the deficit area. That means the energy would be provided by the flywheel to the crankshaft. So we can take this one here, because this may not be less than the velocity at the point C. Why? Because it's already gained so much of velocity here. So compared to point at the, for example, point D, if you take point D and point B, velocity at point B is very less compared to the point D. So if you treat these two deficit areas, this one and this one as equal, then velocity at E always should be greater than velocity of at the C, because this predecessor points B is at the low velocity compared to the point that is prior to the E. D point is prior to the point E, so but this is at the higher velocity, so that it would be something like this, or it can be like this, but still it shouldn't be less than the velocity at point C. So from this diagram, can we say that omega c is the minimum velocity, and velocity at the d is the maximum velocity? And if you draw corresponding block to the bending moment diagram, so this is the point C and this is the point D. So this is the, as we already predicted, this is maximum fluctuation of energy. So what is the maximum fluctuation energy? Here maximum fluctuation of energy is the excess energy area above the mean torque. So this is the green color. So this is the delta E max. So this is how we need to calculate delta E in this case. And how to calculate delta E in case of a multi-cylinder engine. So this is the multi-cylinder engine, and theta diagram is given like this. So this is the point A and B, and the some energy is fluctuating around the torque, mean torque. And we have already seen that E proportional to omega or omega square. So let's draw, and this is directly energy areas are given, that means energy is given. So um, so how to calculate delta E in this case? So for example, if you consider energy or crank speed at point A, first let me draw these points, corresponding point on this one. And if you consider velocity of the flywheel at point A is non-zero, then it is like this. And this is the surplus area. This is surplus area. So flywheel gains the speed or crankshaft. So this is the B point, and velocity of the B is obviously more than velocity at A. And when by the time, for example, if it is starting from some value 0 or omega m, this is the omega m plus 1.6. Let me take this as a 1.6. I mean, I got this, I divided by 100, and omega is equivalent to the or proportional to E, so 1.6. And this is the energy deficit area. So at point C, 1.7 should be subtracted from the 1.6. So that means it's a omega m minus 1.1. So this is 1.1. This is the 1.1 is coming like this. This is the point C, and at point D we have again 1.6. So that should be added to the 1.1. So how much this one? So this become, this is the minus, this is below the omega m. So let me say this is the omega m minus 1.1, and plus 1.6. How much? 1.5 at point D. That is the 1.5. 1.5, and in the same way at point E, 1.5 minus 1.9, that is 0.4. 0.4, this is the point E. And at point F again 1.9 minus 0.5, 0.9. How much? That is 1.5. 1.5. This is again going like this, that is point F. And at point G again 1.5 minus 1.6, that is 1.1 minus value. So in the above this equation, or this diagram, sorry, in the above diagram, omega E is the least angular velocity or minimum angular velocity, and we have so many angular velocities above the W mean, but angular velocity at point B is 1.6. So we say that omega B as the maximum. So area between these two is the delta E, as we already discussed, because delta E is E1 minus E2, and E1 is corresponding to energy corresponding to the maximum angular velocity, and E2 is energy corresponding to the minimum angular velocity. And if you draw this to this one, this is the area and this is E. So area between these two is delta E. So what is the area between these two? So that is delta E between point B and E, that is 160 minus 170 minus 190 plus 190. How much? This is 200 with a negative sign. So maximum fluctuation of energy is 200. That's how we need to calculate. But as I already seen, in every time it's very difficult to draw this crank speed and you know indicating the minimum speed values and maximum speed values at different points, and then drawing the equivalent um, equivalent equivalent one in the bending momentum diagram. This takes little bit of time. So what we can do is simply, instead of drawing this crank speed diagram, what we can do is, since this energy is proportional to omega square, or we can say omega, we can consider energy at E as a random one. For example, energy and point. So if I take point A and I will assign an energy E randomly, and at point B, that is E plus 160, and at point C, that is E plus 160 minus 170, that is E minus 10, and at point D, E minus 10 plus 160, that is E plus 150, and at point E, E plus 150 minus 190, that is E minus 40, and at point F again E minus 1 E minus 40 plus 190, that is G plus 150, and at point G again this is the E minus 10. So what is the minimum energy? What is the minimum energy from all these cases? Point at C, that is E minus 40. And what is the maximum energy? That is at point B, that is E plus 140. So energy at B, that is E plus 160 minus energy at E, that is E minus 40. This is delta E equal to 200. So we got the same answer that we have already deduced by using the crankshaft speed versus theta diagram. So in this way, we need to calculate maximum fluctuation of energy for different diagrams. And let me summarize again whatever we have so far seen. So for example, if the diagram is just like in the two-stroke double acting engine, that means if the T theta diagram is, this is T and this is theta, if if T theta diagram is like this, and if you know the T minimum, T mean, then you calculate this surplus and deficit areas, and whichever area is maximum value, you take that as a delta A with respect to of its sign, whether it could be a surplus area or a deficit area. Or if the diagram is as like in the 4-stroke single cylinder engine. Then you can take directly the maximum value. This is the T mean, and this is the theta, and this is the T. Here deficit, these are all deficit areas. This is the deficit and this is, but compared to all this is the very bigger one. Here I have written, I haven't drawn, showing this as a bigger one, but this as a bigger one area. So directly we can take this as a delta E. That means area above the T mean. This area can be taken as the maximum fluctuation of energy. And in case of a multi-cylinder engine, we have already seen how to calculate. Just now we have seen that one, how to calculate delta E. But here one thing we need to remember, unlike for example, here directly energies are given like this, it is a varying like this in the previous case. So here we cannot take, for example, this is positive and the negative, this is positive, so we cannot take maximum area that is fluctuating around the T mean. Why? Because if you observe in the case of 2-stroke double acting engine, we have calculated the maximum fluctuation of energy by observing the maximum surplus area or deficit area around the T mean. But whereas in case of multi-cylinder engine, we shouldn't do that. So instead we should follow the procedure that I have already explained. So here we should not go for delta E based on the maximum value of this area. That is wrong. So instead we consider E here and the energy at point A, and we add everything and we subtract as just now I have explained. Before we going into solving different examples, here I would like to explain one more concept, that is, for example, in case of a 2-stroke double acting engine, we have points like this. T theta diagram, bending momentum diagram is like this. For example, this is the point A, B and C, D, E, and this is the mean torque, and this is F, G, H, I. And this torque produced in the engine is not constant. If the torque produced in the engine is constant, then vehicle is moving with a constant speed. That means angular acceleration is 0, but this is not constant. So we have angular acceleration. So angular acceleration, this is the mean torque that we need to produce. But in this scenario, when crank rotates from F to B, this torque is increasing. So when torque equal to T mean, there is no alpha equal to 0, that is angular acceleration. But when the crank is rotating from F to B, it's gaining some acceleration because of the increased speed. So the acceleration gain from when the crank is rotating from F to B is alpha gain when torque is T minus T mean, that is equal to I into alpha equal to this is the angular acceleration. This is the acceleration. In the same way, when the crankshaft is rotating from G to C, we this engine or in crankshaft or flywheel will be decelerated because of the deficit area. So here also angular velocity deceleration equal into I equal to here T mean minus T, because here T produced is less than T T mean that we need to produce. So in this way we can calculate this alpha acceleration or alpha deceleration.